Hello and welcome to section 1.5. We are going to talk about evaluating physics expressions in this section. We've already talked a little bit about how in physics we use a lot of models to simplify systems that are very complex. We can't analyze all of the different components at once, so we use models to simplify them. And we're going to talk in this section about the tools of math in physics. In physics, we use a lot of math tools, and they're very powerful tools, and they make it possible to study the things that we're going to study. So some of those tools are tables, graphs, and equations. Obviously, if you had all of this data put all over the page somewhere, it would be really hard to understand what is going on, and it would be a mess. Tables are wonderful because they help to make that data easier to understand, as long as you always label everything and you always put units. Tables aren't very useful if the units and labels are not included. Graphs. Graphs are another incredibly useful tool in physics. They make our data a lot easier to understand. All of this data here was put into this nice graph, position versus time. And this is actually position time graph for free fall. So this is showing, right here, that line, the acceleration due to gravity. And this makes it really easy to see what's going on and helps us to understand different phenomenon. Equations in physics are another indispensable tool. We couldn't do physics without equations. Equations, though, you don't need to be afraid of them. They simply describe relationships between physical quantities. So here are just some different simple examples of different equations that we work with in physics. The relationships between these physical quantities are represented there. Oftentimes, within equations, you'll see some Greek letters. You're going to see them a lot, like delta. That's capital delta in Greek, and it stands for change in. And you find the change in something by subtracting to get that change in, taking the difference between those things. Some examples would be change in position, like change in x or change in y. The change in x would be or y would be those coordinates on a plane. And you find that by subtracting in order to find the difference. Sigma, capital sigma, is a Greek letter, and it represents the sum of whatever is going to follow. And we'll use that also in physics equations sometimes. So how, with all these different letters floating about, how do we find out when a letter represents a quantity or a unit? If you'll notice right here, we have acceleration equals the change in velocity over the change in time. How do we know that these represent different quantities as opposed to a unit? How do we know whether that m represents mass or meters? Well, typically, if the letter is written in bold or in italics, it's referring to quantities or variables. So that m in that previous equation was written in italics, so it was referring to mass. It was a variable or a quantity that it was representing. If the letters are just regular Roman letters, they're not bold or italicized, they're just referring to units. And here are some examples in this table. Meters would be one example of a unit. It's written in regular Roman letters. Seconds in regular Roman letters. Kilograms, regular Roman letters. The symbol for the variable or quantity would be written here. Change in position would look like delta x or delta y, and the y and the x are in italics. Sometimes it's really hard to tell, and this particular, depending on the type and the font, it can be very difficult to tell whether it's italics or not, but these are the general conventions for those rules. Now let's look at some more math tools that you should be using in physics all the time. One is dimensional analysis. And another one we'll just be talking about order of magnitude estimations. These are tools that you'll use to solve problems, also to check problems and make sure that what you're doing is correct. Let's do a little sample problem. Let's say that you are in your car, you're traveling 80 kilometers per hour in that little car of yours, and you're going on a trip, and you're going to travel for 500 kilometers. How long, question mark, how long is that going to take? Okay, how much time? Well, you can use dimensional analysis to solve this. You do not need a fancy equation, and a lot of times in physics it is that simple. Sometimes things are a little more complicated, and you do use your equations. But here, you know that if you're traveling, let's write this again, some distance, you know that that distance in kilometers multiplied by a conversion unit relating the distance and the time. You could put distance on the bottom, right? And you can put time on the top. When you multiply those together, the distance cancels out and you're left with time. So when you actually plug the numbers in, we end up, the kilometers cancel, and we get 6.25 hours that it will take us. Now, when we look at our units in physics, it's important that you always write units. Every bit as important as in chemistry, but maybe even more important, because we're going to do a lot of math and a lot of algebra, and you need to always include the units. They are every bit as important as the number itself. There are two parts to every problem, the magnitude as well as the units. So when we're looking at checking our work, always check the units, always look at the dimensional analysis, and check and make sure you're doing things correctly. The other check that we can do in physics, order of magnitude estimations. And that's a quick way. We're going to look at an example with what we've just looked at so far with this 80 kilometers an hour going 500 kilometers. Obviously, this is really simple and it's not too hard to figure out in your head, but when problems get more complex, the order of magnitude estimation is a really useful tool. So we'll walk through it with this example. We know that if we look at our 80 kilometers per hour and our 500 kilometers per hour, let's look at our distance first, the 500. Is 500 closer to 10 squared or 10 to the third? You know 10 squared is 100. You know that 10 to the third is 1,000. So 500 is actually closer to 10 squared. That is the order of magnitude that it is closest to. Now let's take a look at our number 80. Is that closer to 10 to the first or 10 squared? We know 10 to the first is just 10. 10 squared is 100. So 80 is closer to 10 squared. That's about the order of magnitude, the range that it falls within. Well, when we look at our calculations and we take our distance value, which is the 500, that would be the 10 squared. We are going to multiply that, remember up here, by the time over the distance. That would be the same thing as the inverse of 80. Would be multiplying it by 1 over 80, or simply dividing by 80, which is going to be 10 squared. If we take 10 squared divided by 10 squared, we just get 10. Well, is 10 pretty much in the range of our answer, 6.25? Yes, it is. It's about that order of magnitude. 6 is actually closer to 10 than it is to 1. So that is the correct order of magnitude, and order of magnitude estimations are useful in checking your work. Do you want some advanced work to do? Get an advanced proficiency? Try estimating the thickness of a page in your textbook by using these tools of mathematics that we've been discussing, measuring the thickness of all of the pages in your textbook. And does your answer make sense? Go ahead and walk through the checks, checking by dimensional analysis and checking by order orders of magnitude estimations and seeing if you're correct. So look forward to seeing you in class.